Okay, we have analyzed the free electron approximation, but of course that's not enough in order to describe physical properties of a solid. And we need to go beyond that. And the first approximation that we can consider is the Hartree approximation. And here I'm going to give you a general description of the Hartree approximation. We'll apply that later to the homogeneous electron gas we want to analyze. So let me remind you that our first goal is to get the eigenstates, eigenvalues of the Hamiltonian. This is like a complete Hamiltonian we have in our system. Here we have the kinetic energy associated to the electrons. We have the electron-ion interaction, which is usually we call it U ion. Here we have the electron-electron interaction. Here it doesn't appear the ion-ion interaction because this is just basically a constant and it's not important to get the wave functions here. So within the Hartree approximation, we have two important features. It's based on two important features that we're going to analyze now. First, we'll keep the independent electron picture, but the wave function that we're going to consider in this approximation is not going to be antisymmetric, even though we might consider later that the Pauli exclusion principle is going to fulfill and its state is going to be doubly occupied because of the spin. Of course, within this Hamiltonian, we cannot apply, of course, the independent electron picture because the electrons are not independent here. But within that approximation, considering that, we are looking for some kind of effective potential that each electron is feeling. This effective potential could be caused by all the rest of the electrons. And considering that effective potential, the electron could be moving like independently of the others. This is the idea behind this Hartree approximation and this independent electron picture that's made in the Hartree approximation. And considering that independent electron picture here, it means that the wave function that we're going to try here is that the product of the wave functions of individual electrons. So this is like the first step. And second step here is we're going to apply the variational procedure. But let me remind you that looking for stationary states of the average Hamiltonian of an unconstrained wave function, it's actually equivalent to look for eigenstates and eigenvalues of the Hamiltonian. So here we are not going to find stationary states of unconstrained or of average wave function or average Hamiltonian using unconstrained wave functions, because we are going to use a particular form of wave function which is independent electron picture. But we may think that's going to be a very good approximation to find the stationary states or to find the energies or the eigenstates or the eigenvalues of the Hamiltonian. So according to that, our first step is going to be to calculate the average Hamiltonian, considering that wave function. And for that, it's important to remember that the scalar product of those two wave functions, we're making the scalar product of these two wave functions besides making the integration of the space. As we have spin state here, we have to do the summation of the spin states as well. So the first step here is to have an expression of the average Hamiltonian considering that wave function here. And that is what we have here. That's the average Hamiltonian. Okay, it's important to check that. It's important. You have to check that this is all that's correct. Here it's important to distinguish the different terms arising here. Here we have the contribution to the energy coming from the kinetic energy of the electrons, electron-ion interaction, and then we have another term here. This is coming from the electron-electron interaction. And actually, we can have it can be understood using like a classical picture. For that, let me remind you, if we have an electron, which is if the electron wave function is psi, represented by this one, the priority density of this one is going to be this. If we want to sum over sigma, different sigma state, that's going to be the priority density of the probability of having an electron position R, which is going to be equivalent to a charge density. So just corresponding to electron I. If we sum over all electrons we have, if we sum therefore over all I states, we have, that's going to be the complete charge density associated to a system which is represented by this kind of wave function, for a wave function where we have a product of P1, P2 wave functions corresponding to its electronic states. So here in this integral here we have a summation over J and I states. So summing over I states or summing over J state, will have the summation over I state and summation over J state and the summation over I and sigma and J and sigma prima. That will be the charge density at R prime, and that will be the charge density at point R. So basically what we have here is the interaction energy in whenever we have a system which is characterized by a charge density at R. So the interaction potential of a system with electronic density and N is given by that expression. So this is like, that's given to us, therefore, the contribution or the understanding of this last term we have here. However, it's important to remark that here in the summation, same states are not included in the summation to avoid like a self interaction. So we have to minimize that contribution here, that expression here, with respect to the wave functions we are using in that average, in the calculation of the average of the Hamiltonian. But the wave functions we are going to use here have a constraint. They have to be normalized, which basically means that the wave function we have for each electron has to be normalized. So whenever we are doing a minimization with a constraint, we have to use a Lagrange multipliers method, which basically means that we have to define a new function. In this case, we are going to call it f, which is the function that we want to minimize, which is all this expression here, then minus different terms with Lagrange multipliers times the constraint that has to be fulfilled. In this case, of course, we do not have just one Lagrange multipliers. We have as many as electrons we have in the system. We have n Lagrange multipliers because we need to fulfill n normalization condition corresponding to the wave function of each electronic state. So that's the wave function that we are going to minimize, and the minimization is going to be either with respect to the Lagrange multipliers we're going to do, and doing the minimization with respect to the Lagrange multipliers, we're getting therefore this expression to be 0, which means that this equation here is going to be satisfied. Besides that, it's an important thing, we are going to do the minimization with respect to these wave functions, which appear here and also here. And doing that, we need to do a functional derivative. And we are going to do the functional derivative either with respect to psi or psi complex conjugate, because we could consider that they are like independent, different wave functions. Actually, let me remind you that these plane waves, actually, they are completely different. Actually, they are orthogonal wave functions. So we can consider that these and these are independent variations. And in this case, for getting that Hartree equations, we're going to do the minimization with respect to the psi complex and looking for stationary states, we are going to make that functional derivative to be 0. And doing that functional derivative to be 0, we are getting the Hartree equations. And these are the Hartree equations we are getting if we are doing that. These are the Hartree equations we need to solve in order to get the wave functions, this Ci, the wave functions corresponding to each electron. So that's the wave function, that's the equations that we need to solve. Actually, if you look at the wave functions, they look very similar as the equations that arise whenever we have to solve the eigenstates or eigenfunctions of the Hamiltonian. They look very similar. Actually, analyzing different terms here, we can see that the first term it's somehow related to kinetic energy associated to the electrons. Then we have the electron-ion interaction. And then we have this term here, which actually, as we have said before, this term here, whenever we are doing the summation over J, is giving to us the electronic charge density. So this is like the interaction potential that electron I can see and caused or induced by all the rest electrons we have in the system. So this is what we were looking for. This is like the effective potential that electron E can see in the system and caused by all the rest of the electrons we have in the system. And the effective potential here, it's what's doing. They are screening. So it's important because we are introducing here the concept of screening. All the electrons are screening the potential created by the ions here. So that's the kind of understanding we have for the Hartree equations here. That the Hartree equations are extremely complex to solve. They are non-linear. You can see that here we have the C square. And of course, in order to get that effective potential here, first you need to know which are these wave functions. And which is, of course, that's extremely complex to solve this kind of equations. Usually the methods followed to solve it is a self-consistent method, which basically means that you start with some initial guess for all the wave functions, and you plug that initial guess here in order to solve and get an initial expression for the effective potential here, and using that initial expression for the effective potential, you solve that equations here for the new Ci. Once you have the new Ci, you recalculate the effective potential, you get a new effective potential, and considering that new effective potential, you calculate again and get the new Ci functions, and so on and so forth until you get the required convergence. But even though it's quite easy to say so, doing that analytically, doing that numerically, it's quite complex, because in general, for example, you have to do that integration here and depending on the system, but if you don't have any special symmetry in the system, doing that is extremely complex. So, okay, so even though we made the independent electron approximation, as you can see here, Hartree equations we are getting to solve that system. It's not going to be easy at all, but that's kind of the first approximation we have beyond the free electron-like approximation. Okay, the next step will be to apply this Hartree approximation we described here within a general context for the homogeneous electron gas we are considering as a first approach to describe a solid that, even though it's simple, you can see it's quite challenging as well.